All right, folks, this is section 7.2. We're talking about addition and subtraction formulas, sometimes called the sum and difference formulas for sine and cosine. And these are the formulas. Okay, so there's two versions. Here's the sum formula for sine. Okay, and here is the difference formula for sine. And then the sum formula for cosine and the difference formula for cosine. My suggestion, pause the video, write those down, have them at your disposal. They're very similar, very hard to remember. A couple strategies I use, for instance, this is one, sine of s plus t. So if it starts with sine, I know the pattern goes sine, cosine, and then sine, S-I-G-N, that goes with the sign that was chosen here. And then cosine, and then sine. So it goes sine, cosine, sine, S-I-G-N, cosine, sine. If it's cosine that you start with, then I know it goes cosine. I'm going to say cosine 3 times. Cosine, cosine, and then cosine. And when I say cosine here for that, it's actually the opposite of what that was. So the co idea meaning opposite. So it goes cosine, 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 and then finishes sine, sine. Develop some tool for you to learn those. They're going to become essential for us. These I don't so much know off the top of my head because if I need them, I'm going to take that sine, which is this thing here, divided by that cosine, which is this thing here. So I'll take that divided by that, run through a little bit of algebra, and I generate these two on my own. What this is going to allow us to do right now, we don't know like exact formulas for sine. If I were to ask you sine of 60, you automatically right away know it's radical 3 or 2. Okay? But if I ask you the sine of 75, you don't know what that is. But you can say, well, I know the sine of maybe 75 is the same as 45 plus 30. That's still 75 degrees. And what happens then is you see this would be like your S, and this would be your T that is being used over here. And you can break this down to say, now, well, I know what sine of 45 is, cosine of what will be 30, plus then cosine of 45, and then sine of 30, and you know what each one of those are. So if you know what each one of those are, you should be able to evaluate and kind of come up with the exact value for sine of 75. Okay, so what I want to show you then is how this is generated, how this formula is created.
Please?
Alright, so in GeoGebra here we'll kind of demonstrate how this formula is created. Alright, so first thing we're going to do is we're going to start with arc T here. Alright, so that arc T, obviously we're in the unit circle here, so remember that T is the same as the central angle here. When we have that, this point, whatever it is, if T is pi over 4, that point is the cosine of pi over 4 comma sine of pi over 4. And we can keep doing it no matter what T is. And, T could be pi over 6, it could be pi over 3, or sorry, it's just be pi over 6, that'd be pi over 3, but it doesn't matter. So that is kind of the ordered pair that is defined by using an arc of T. What we're then going to do is we're going to attach a new arc to it, and it could be the same as T, but it's probably usually different. Call it S. Okay, so now if I go this arc right here, that total arc would be S plus T. So in the unit circle, that point would be called cosine, or be identified as the cosine of S plus T, comma the sine of S plus T. Okay, so that's nice. So what we're looking at then is a way to generate that ordered pair through the use of knowing that thing right there and ultimately this one down here. I put this one in, that's the arc of negative S, okay, which this would be cosine of negative S, comma sine of negative S, and we don't like negatives as our argument, so this is a great use of our even odd properties. So we can write cosine of negative S as just the cosine of S, and the sine of negative S is the opposite of sine of positive S. Okay, so with this structure here, if I look at these arcs and just kind of trace over the top of them or highlight over top of them, this arc right here Let's get that a little bit bigger. That arc right there is s plus t, and that blue arc is also s plus t. So these arcs are congruent, and that's what we're looking for. That's the feature that allows for some nice geometry here. Because if arcs are congruent, back to geometry, that is the chord that goes with that first arc. We call that the subtended chord, or we call the arc the subtended arc. It's just that these two things are kind of paired with one another. Okay, either the chord makes the arc, or the arc makes the chord, however you want to view it. This would be the chord for this second arc. Well, the thing about this is that those two arcs, s to t and then t to negative s, those two arcs are the same. And if you remember from geometry, if the arcs are the same, that chord and that chord should be the same. Okay? And that's what we're seeing here. So, what do we do? Okay, how can we generate those formulas that we just recognized? So what I'm going to do, if these arcs are the same, I'm going to use the distance formula. You remember the distance formula? The distance formula says, I'll just write it up here, distance is equal to the change in x, quantity squared, plus the change in y, quantity squared. Okay, so I'm going to do that with these ordered pairs. First one I'm going to do is I'm going to do P1 to P0. Okay, this is going to get messy, so I apologize if I run out of room. Just the way it is. So P1 to P0. So I'm going to go cosine of s plus t, that's this x coordinate, minus that x coordinate, so minus 1. And I'll square that. And then I'll do the same thing with the y's. So sine of s plus t minus that 0, and we'll square that. So that's the distance from P1 to P0. Now I'll do the same thing from Q1 to Q0. Okay, so cosine of t minus then that cosine, so be cosine of s, and we'll square that. Then we're going to add to that, okay, the difference in the y's. So that sine of t minus then that sine of s. So minus a negative sign turns into a positive, and we'll square that. Okay, so that's what we're looking at here. Now here's the thing. Like I said, those chords are the same, so that distance and that distance are the same. So these radicals are the same. But if these radicals are the same, that means their radicands have to be the same. So I'm just going to get rid of the radicals here, and I'm going to put these things equal each other. So let me generate a little bit more room here and move in this thing over. Alright. So, and this is kind of where things could get messy. So again, I apologize. I'll try to write small enough so it doesn't run off the page. We're going to have that top radicand, so cosine of s plus t minus 1, that quantity squared, plus then the sine of s plus t, that quantity squared, is equal to now the bottom radicand. So the cosine of t minus the cosine of s squared, plus then the sine of t plus the sine of s, quantity squared. Okay. Now it's just about doing a little bit of algebra. Okay, so I've got these squares of sums and differences, so I'm going to expand those. Okay, this is just using this rule here. If I've got a plus b squared, that turns into a squared plus 2ab plus b squared. So I'm going to use that several times here. First one is with cosine. So we have cosine of s plus t. It'll be squared now. Okay, and then I'll multiply these two things together and double it. So minus 2 cosine of s plus t. And I'll square that negative 1, so it becomes positive 1. And then I'll do the same. So this here doesn't, it's obviously not a sum or a difference squared, so this just becomes, or stays, sine squared of s plus t. Over here on the right hand side, do the same thing. So this becomes cosine squared t minus then 2 cosine s. Let's put t there first because it doesn't really matter, but let me see here. I'll make that a t. So I'm going to multiply those two things together and then double it. So then be cosine of my s. And then square that back term. So it'd be cosine squared s. Over here, do the same thing with this. So it'd be sine squared of t plus then 2 sine t sine s. And then square the back one. So it'd be plus sine squared of s. Now it gets messy, but there's some nice things that happen here. So some nice things that first occur, I'm just going to go through and highlight them, is that we've got a lot of sine squared plus cosine squares. So, and it doesn't matter what the argument is for those, as long as the arguments are the same. So we've got this idea here. If I take that term and that term, okay, that's a sine squared plus a cosine squared, okay, of the same argument. So that turns into 1. Here I've got a cosine squared t and a sine squared t. So that turns into a 1. We've also got then on the right hand side a cosine squared s and a sine squared s. That turns into 1. Okay, so I'm just going to go through and rewrite this stuff with those things changed to 1. So it's going to be 1 and then minus 2 cosine s plus t plus 1 on the left hand side. Okay, on the right hand side I've got so that would have given me a plus 1, and then this would have given me another plus 1, so I'm just going to say plus 2. Okay, and then we've got minus 2 cosine t cosine s plus then 2 sine t sine s. And what happens here now, if I combine these, I get 2 minus 2 cosine s plus t equals over here 2 minus 2 cosine t cosine s plus 2 sine t sine s. The nice thing is that 2 and that 2 cancel, okay? And when that happens, everything else is divisible by -2. So when I divide everything by -2, it's going to be cosine of s plus t. Divide this by -2, it's going to give me a cosine of t cosine of s. Divide this by a -2, and so give me minus sine of t sine of s. And then usually what happens, just to match the form, to make it easy to remember, we usually write this as cosine s plus t, and then put these in the same order. So it'd be cosine s cosine t minus then sine of s sine of t, and it just allows us to jockey those around. Okay. What then happens to get the cosine of s minus t is that we say, well, cosine of s minus t is the same thing as cosine of s plus a -t, and then we go through and say, well, okay, that becomes cosine of s cosine of -t minus sine of s sine of -t. And we use our even odd functions, and our even odd functions are essentially going to keep that as cosine of t, so I can rewrite that as cosine s cosine t. Now an even odd function, this was a -t here, I know the negative ran together here, but that becomes a negative out front, and I can write it as now plus sine of s sine of t, and that then becomes the cosine of s minus t. Okay. If we have time, and maybe the next video, I'll go through and show you how the sine sum and difference are created, and it's a practice on knowing the sine and cosine cofunction relationship. Okay, so let's go through and actually do some example problems now of this stuff. But first, I'm going to take care of my 1-year-old. So give me a second. All right, so before we go to the examples, though, I just want to reiterate, you're not going to necessarily need to know how to do this, okay? It is algebra that you are familiar with, but as always, I don't like just giving you these formulas here and saying, just take my word for them, okay? I want you to know that how they are derived, where they come from, and you know, it's good practice to maybe see some of those, the use of the cofunctions, or not cofunctions, even odd, and we'll see the use of the cofunction when we prove how these are created. All right, so let's get to talking about like what we're actually doing here. It says find the exact value of each expression. So a couple things that I would do just to make things easier for yourselves is I would not necessarily do this with radians per se. I would do everything with degrees and then work back into radians when I'm done if I need to. And you shouldn't need to. You should always, once you change these into degrees, you're good to go from there on out. So I kind of give the examples here. And there's just this example. Let's just do this cosine of 75, and we'll also do the sine of 75 as well. Get used of both those formulas. So what does this mean? It means if I obviously from the unit circle don't know what cosine of 75 is. So what I'm going to try to do is use the angle measurements off the unit circle that we're aware of, and it could be any two, as long as they add or subtract to give you 75 degrees. So the ones that come to mind, I think, to me first are 30 degrees and 45 degrees. Obviously, those add together to give me 75. So what we're going to do then is we're going to see what that turns out to be as an exact value. So I'll go cosine. So the cosine formula goes cosine, cosine, cosine. So this is a positive, so it's going to go minus. And then it goes sine, sine. You notice I left the arguments blank because when I'm done, when I do that, I get the general structure. It's just then those two angles, 30, 45, 30, 45. Okay? And now we should be able to evaluate. You guys know what the cosine of 30 is. It's radical 3 over 2. You know the cosine of 45. That's radical 2 over 2. Minus then the sine of 30. So the sine of 30 is 1/2. And the sine of 45, radical 2 over 2. If I multiply this stuff together, this gives me here radical 6 over 4. Radical 6 over 4. And this here gives me negative radical 2 over 4. So this, if I wanted to write it this way, common denominator of 4. So there is the cosine of 75. So at 75 degrees on my unit circle, so maybe 75 degrees is right there. The x-coordinate is this amount. That's the exact value. Okay. So let's do the sine of 75 then, and then we'll go to GeoGebra or Desmos and see if this makes sense. So then cosine of 30, cosine of 40. So we use 30 and 45, I guess. So it makes sense again down here to go sine of 30 plus 45. And now I'm going to set up the general structure for sine. So it goes sine, cosine, sine, S-I-G-N, and it's the sign that I use there, so plus. Okay, so sine, cosine, sine, cosine, sine. And then again, just go back in and put 30, 45, 30, 45. So sine of 30 is 1/2, cosine of 45, root 2 over 2. So they're getting multiplied together there. Plus then cosine of 30 is root 3 over 2. And sine of 45 is root 2 over 2. So that's going to give me then, when I multiply that out, radical 2 over 4 plus radical 6 over 4. So radical 2 plus radical 6 all over 4. So 75 degrees. So cosine, I just want to say cosine. Let's just say the angle measurement theta equaling 75 degrees has the ordered pair of x being radical 6 minus radical 2 over 4, and the y would be radical 2 plus radical 6 over 4. And we should be able to justify that using Desmos. So let's get that up. We'll put this in degrees because obviously that's what we're using. And now if I just type in, so I'm going to type in cosine of 75. Gives me that number right there. Okay, so then I'm going to take what we found for the cosine, which was the radical 6, so square root of 6 minus square root of 2 all over 4. And you see that that number and that number are identical. Okay, so that's the exact value then for the cosine of 75. We do the same thing for sine of 75. Gives me 0.965. So then I'll go square root of 2 plus square root of 6. And we will divide all of that by 4. And there you get your 0.965 number. Okay, so we can do this with anything. We can do it with basically go around your unit circle, take any two numbers off, add them together, or subtract them. And generally what's going to happen is this is going to fill in, because we know multiples of 30 and multiples of 45 all the way around the unit circle. Well, this is going to fill in then, because I can take a 30 and a 45 and I can subtract them, or I can add them. And what that's going to do is give me the 15-degree increments. So I'll know all the way around the unit circle by 15 degrees, which is a nice thing. Okay. If they ask me to do the same thing for this pi over 12, so I give a little bit of room over here. So it says find the cosine of pi over 12. Okay. My suggestion to you, don't do it in radians. It's going to be hard to think about in radians. But we know pi over 12, you can multiply that by 180 over pi. Okay, so that should give me 180 over 12, which ends up being 15 degrees. So cosine of pi over 12, same thing as cosine of 15 degrees. Now what I would do is say, okay, well, how can I rewrite cosine of 15 degrees? Well, isn't cosine of 15 degrees the same thing as maybe 45 minus 30? That's another way of getting 15 degrees. So then I'm going to say, well, that then expands to cosine cosine, remember that third cosine is the opposite of that symbol there. And then it'll go sine. And I just go plug in my 45, your 30, your 45, and your 30. So now cosine of 45, radical 2 over 2. Cosine of 30, okay, radical 3 over 2. Plus then sine of 45, root 2 over 2, sine of 30, 1/2. So I get radical 6 over 4 plus radical 2 over 4. And you're going to find out that you get a lot of similar answers. Obviously, the cosine of 15 and the cosine of 75, there should be relationships between those ordered pairs. If I go back to the unit circle, remember, if we were looking at like 30 degrees and 60 degrees, they were reflections across the line y equals x. So if I had a comma b here, this would become b comma a. Same thing for then 75 degrees and 15 degrees. Okay, so in the last one we saw that the y value for 75 degrees was actually this. Now that becomes the x value for 15 degrees. So just double check it real quick. Let's go back to Desmos and let's do it in radians. So put radians in here and type in cosine of pi over 12, and it gives us that number right there, which we found out to be radical 2 plus radical 6 over 4, which you see then that they are the same. So that's the use of the sum and difference formula. It helps me find those exact values of those angle measurements. Okay. This next question is just the reverse of that. They give you the expanded version. So what you got to do is realize, okay, if it goes cosine, 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 then that is the expanded version of cosine of ultimately, if I use a and b here, it'd be a and b But because that's a minus sign, this can become a plus sign. So the A here is 14. So cosine of 14. The B is 46. So what's 14 plus 46? That's going to be 60. And now, in this case, we know what the cosine of 60 is. Cosine of 60 is 1/2. So let's just check to see if that actually makes sense. If we go back to Desmos, type in cosine of 14 degrees times cosine of 46 degrees minus then sine of 14 sine of 46, we see that it does indeed give me that 0.5. Example 3, just proving a cofunction identity. And we've done this, we've proven this other ways using translations, okay? Using phase shifts and cofunctions, even odd properties, that kind of thing. So now let's do this. So let's use this sum difference formula. So I've got cosine of pi over 2 minus u. Well, that's cosine. So it's going to expand this way, cosine, 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 and then sine, sine. And then this will be pi over 2, this will be u, pi over 2, u. And the nice thing here that happens, what's the cosine of pi over 2? What's the cosine over, at that point right there? That's pi over 2, right? What's the cosine or the x value? It's got to be 0. So that goes to 0 times cosine of u plus then, well, the sine of pi over 2, what's the y value of pi over 2? That's 1. It'll be 1 times sine of u. Those go away. 0 times anything is 0. So we get 0 plus 1 times sine u, which is just sine u. So we just have proven in an alternative way the cofunction relation between cosine and sine. These tend to be the harder of the problems that people come across. Basically what happens here is you're going to have to, you've got alpha minus, this is phi, okay, or not alpha, that's theta, theta minus phi, but they're just your angles, okay. So what we've got here is a general theta minus phi, which is going to turn into, it's going to expand as cosine, 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 sine, sine, and then this will be theta, this will be phi, theta, phi. The only thing is that we don't necessarily know what theta and phi are, okay, or the cosine of them. What's nice here, though, is that we do know that cosine of theta is 8/17. So we can replace, and what's important here for us to understand. All right, so what we're going to find out here is that the cosine of theta is 8/17. So I can replace that whole thing, not just theta, but cosine of theta with 8/17. Okay. Now I can't replace any of this other stuff because I don't know what this other stuff is. But this information there and that information there give me information that I can come up with the cosine of phi, the sine of theta, and the sine of phi. So we've got to draw a picture though. Okay. So I'm going to draw a picture here for theta, and I'll draw a picture over here for phi, and then we'll go back and capture what those values are. So cosine of theta says 8/17, but theta is in quadrant 4. So here would be theta. Remember doing this process. Cosine is 8, so that's 8 adjacent. So adjacent over hypotenuse. So 8/17. Okay. So this is, it's a Pythagorean triple. Okay. So if we take 17 squared minus 8 squared gives me 225. Square root of 225 is 15. And now because we're in the fourth quadrant, that 15 is negative. Now we're doing phi. Phi says the tangent is negative root 15. But we're in quadrant 2. So we're in quadrant 2. So that's phi. And remember, tangent of phi is equal to sine of phi over cosine of phi, which, if we think about sine as your y value, cosine is your x value. Okay? So when we have this root negative 15, it's over 1. This is my y value. So negative, or let's say radical 15 is that y value. And then 1 is the adjacent side, or the x value. Now which one of those has got to be negative? That's the one that's got to be negative. Okay. Then when we go through and we use Pythagorean theorem here, we can say 1 squared plus root 15 squared should equal my hypotenuse squared. So it gives me 16 is equal to the hypotenuse squared. So this distance here is 4. Okay. So why do we have to do that? Because now with those triangles and that information, we should be able to figure out what cosine of phi is. Come over here, cosine of phi is the adjacent side divided by the hypotenuse. Adjacent divided by hypotenuse. So this thing here becomes negative 1/4. Okay? Plus then sine of theta. Well, sine of theta, come over here. Opposite over hypotenuse. So negative 15/17 times sine of phi. Well, phi here, opposite over hypotenuse. So root 15 over 4. Okay. Now we're going to multiply this together, so we get negative 8. So this is going to give me, what, 68 on the bottom. Minus then 15 root 15 over 68. If you want to go ahead and combine this to negative 8 minus 15 root 15 over 68, that's fine. But that then ends up being the cosine of phi minus, or theta minus phi. Okay. Now there is a way to check this. So let's just go to, it's kind of a complex method, but it'll work. We'll come here, delete all of this. So we know that we're in the fourth quadrant here. So I'm going to, with theta, so I'm going to try to take this information here that we have and figure out what the actual angle measurement for theta is. So let's do this in degrees. We'll go cosine inverse. We'll go cosine inverse of 8/17. So 8/17. And it's going to give me 61 degrees. Now that 61 degrees is this angle right here. Okay, remember we're in the fourth quadrant. Okay. So what I'm going to do is take 360 minus that, and it gives me that number right there. So 298.07. Okay. I'm just going to double check real quick. If I take the cosine of that number, let's just call that number A for now. If I take the cosine of A, that should give me the same thing as 8/17. And you see that it does. Okay. So I know that when they are talking about this theta, and let's actually call it T for theta. When they're talking about theta, they're actually talking about this angle right here. Okay. When they talk about phi, let's go to phi here. We're in the second quadrant. We're looking at, let's go arc tangent of negative square root of 15. Okay, so now just because of how the tangent inverse works, So because of the inverse tangent, this angle of -75 that GeoGebra's gave back, or Desmos gave back, is actually that angle. But we're in the second quadrant, so we're going to use vertical angles, and we will figure out that I need to take ultimately 180 minus the positive version of that, but using properties of addition and subtraction, we can get that. And that should give me, again, remember, negative square root of 15 is that number there. So then I should be able to take tangent of, let's call this number P for phi. If I take tangent of P, you see that gives me the same amount. So I know, per the information that was provided, that this angle theta is 298 and the angle phi is 104. Okay, how does that help me? Well, let's do this. Let's take the cosine of theta minus phi and see what it gives me. It gives me that number right there. Well, that should be this number here. So let's take that number. Negative 8 minus 15 square root of 15 all over 68. And you see that those two numbers do indeed then pan out. Okay. That check, I think, is a messy thing to do, especially if you only watch this one time. I would pause it, revisit this. Okay. There's a couple examples in your homework that is going to cover this. I would suggest maybe trying to check on those. So these examples, just to save a little bit of time, these are the same as before. So these are example 5 is using I guess we'll do this because this is a tangent. I wasn't paying attention to this tangent. So your tangent formulas are found, and I'll just save time here. If you want to go through some of last year's videos, you can find it. But the tangent formula here, that one, is found just by taking the sine of this one and that one and dividing them. Okay? So it's tangent of S. So it's let's go, tangent of S plus T is equal to tangent of S plus tangent of T over 1 minus tangent of S times tangent of T. Okay? As we look at this formula for the tangent, come back up here real quick, you see that this is a plus sign and that's a plus sign. So the numerators are the same sign. The denominator then changes to the opposite. That's a minus, top's a minus, denominator changes to the opposite. Okay, so that's just a kind of a quick way of maybe remembering what the signs are. Alright, so if I look at 17 pi over 12, and I don't like that number. 17 pi over 12, I don't like that. So what I'm going to do, I'm going to change it to degrees. So take 17 pi over 12, and we're going to multiply that, remember, by then 180 over pi. It gives me 255 degrees. Okay, so 255. So we're going to take our unit circle and start thinking about things on the unit circle that are going to add to 255. Okay, and right away I see, so 255 minus 120 gives me 135, and those should be 135 and 120 are two values off the unit circle that we know. Okay, so that's what I'm going to do. I'm going to go 255 and 120. So the tangent of 255 is equal to the tangent of 120 plus 135. Okay, so that's going to be then filling this in, tangent of 120 plus the tangent of 135 all over 1 minus the tangent of 120 times the tangent of 135. Now, the only thing is, do we really know what the tangent of 120 is and tangent 135? Well, remember 120 is right there, okay? So the sine of that is, or the cosine comma sine of that, the ordered pair, is what, negative 1/2 root 3 over 2. Okay, so that's 120. So then the tangent of that would be the y divided by x. So it would be, what, negative radical 3. So that number right there is going to turn into negative root 3. Okay? Plus then tangent of 135. Well, if you remember 135, that's right there, and it's negative root 2 over 2, comma, root 2 over 2. So when I take the tangent of that tangent of 135 is negative 1. So then on the bottom, I'm going to have 1 minus then negative root 3 times then tangent of 135, which was negative 1. So now I get negative root 3 minus 1 up top. And so this is going to be, so that product there is radical 3. So we got 1 minus radical 3 there. I think what you can maybe see here, if I take a negative out of the top, factor a negative out, gives me root 3 plus 1 down here on the bottom. I guess I was seeing if these would cancel or anything. They don't. So that's the tangent of 17 pi over 12. So let's, again, double check this. In these situations, your calculator is going to be useful to you. So I'm in degrees, so that gives me 1 there. So these do cancel. Maybe, let's see, negative square root of, we want tangent 255. 255, sorry. So those don't cancel. Okay, so I get that. Okay, so then does that match up to negative square root of 3 minus 1 all over then 1 minus the square root of 3, and you see then that those two decimals are the same. So this is the exact value of tangent of 17 pi over 12. I'll skip this proof of this identity. It is just like this one up here that we did here, number 3. Example number 3. It's just showing the sine relationship with cosine. Number 7. These are a little bit more difficult. They're more arbitrary because they don't have exact values in here. When we use our inverse information, guys, so remember that is a ratio. That y is a ratio. So what I'm going to do is I'm going to draw a picture for that ratio of x over 1. Okay, so I'm going to assume, because the sine inverse is only going to happen in these two quadrants. Okay, that's the place that's it. Remember, the range goes from negative pi over 2 to positive pi over 2. So that's the opposite. That's hypotenuse. Working through the Pythagorean theorem, then this should be, so I should be able, let's call this segment here A. So then, what we say, a squared plus x squared should equal 1 squared. So then a squared will be 1 minus x squared. So this a is going to be the square root of 1 minus x squared. Okay. The next thing I want to do is do the same thing for y, though. Okay. So now that's y over 1. So that's opposite. So that's y over adjacent. So that's 1. Okay. So then this distance here would be the square root of y squared plus 1. Okay. So now let's think about what this does. This sine inverse, remember, is going to basically produce this angle here. I'll just call that angle alpha alpha. Tangent inverse is going to produce that one there. I'll just call that beta. So this thing here just turned into cosine of some alpha minus some beta. Okay, well, what does that mean? That means the cosine of something, so it's cosine, cosine, sine, sine. And remember, alpha, beta. So let's see what the cosine of alpha looks like here. If I go cosine of alpha, remember that's adjacent divided by hypotenuse. So that's just going to be that root 1 minus x squared. Okay? Times then cosine of beta. Well, cosine of beta is adjacent divided by hypotenuse. So it would be adjacent divided by hypotenuse. So it would be root y squared plus 1. Plus then sine of alpha, that's opposite over hypotenuse, so x, times sine of beta, which would be y, over root of y squared plus 1. Okay, so this is going to get nasty, but we got the square root of 1 minus x squared over root y squared plus 1, plus then xy over root y squared plus 1. So if I want to clean this up, we could say that this is xy plus root 1 minus x squared all over y squared plus 1. And what that does is it removes the use of, it basically takes a trigonometric function or equation and puts it into purely algebraic form. There's no trig functions left over. So let's just see if we can see that these things are the same. So I'm just going to graph both of them. All right. So I'm going to say cosine of the arcsine of x minus the arctangent of y, and I figured that would be the case. So Desmos doesn't like the implicit nature of that x and y there. So let's do it. Let's see if we can go to GeoGebra and do this. So I apologize. I had to pause and try to do a GeoGebra. GeoGebra wouldn't let me do it. It introduces a multivariable function, which I would be able to see in 3D, but my graphics card will kind of cancel it out or close the program. So figure out how to do it in Desmos. You just got to type in y equals, and then it is okay then with the implicit nature of it. But if I graph the red one, okay, which is what we started with, so it's y equals that stuff, and then do the same thing for the green one. So that's what we came up with algebraically, and you see then that they are indeed the same curve. Thus, we have then demonstrated that this is in terms of sine inverse, tangent inverse, cosine. This one is just in terms of x and y. Okay, so there are like computer applications, programs, a lot of technology that this would be maybe appropriate. Maybe we gather this information, this data somehow, and then to actually work with that data, the computer would change it and use it in this format. Okay. You could think about, if you say like, 1/2 here, and let this be some number, maybe radical 3. Then you should be able to say, well, if I let 1/2 and radical 3 be these numbers, those two things should evaluate the same way. Okay. We'll prove the following addition formula. So that's the sine and cosine addition formulas later. This is a specific example of what we just did here. So I'll skip over that for now as well. Remember, as we do this stuff, there are again a lot of videos on my website that are additional examples that you can go through and use to assist.